Hello everyone, welcome to our channel VLSI Learn with Fun. Let me start with something crazy. Every single chip you use today, your phone, your laptop, even a GPU inside NVIDIA systems, all of them have billions of transistors packed into something smaller than your fingernail. Now here's the real question. Do you think engineers just randomly place all of that logic and hope it works? Absolutely not. There is one stage that decides whether that chip becomes a masterpiece or a complete disaster. That stage is floor planning. Floor planning is not just placing blocks. It's like designing an entire city before construction even begins. You decide where roads go, where power flows, where buildings sit, and how everything connects. And once you decide that, everything else is forced to follow. If you mess this up, routing fails, timing fails, power fails. And guess what? The company loses millions. So don't think of this as just another topic. This is where a chip is either born correctly or broken forever. Now look at this roadmap. At first glance, it looks like just a list of topics. But actually this is a story. We start with where floor planning fits in the physical design flow. Because if you don't know the context, nothing makes sense. Then we move into geometry, die, core, I/O. Basically, what space are we even working with? Then utilization and aspect ratio. How much are we packing and how are we shaping it? Then comes macro placement. This is where real strategy begins. One wrong move here and congestion explodes later. Then I/O placement. This is how your chip talks to the outside world. Then power planning. This is life and death, no power, no chip. Then IR drop, electroigration. These are silent killers. Your chip may work today and fail after 6 months. Then timing and clock, this performance. Then congestion and DFT, this is practicality. Then advanced nodes, signal integrity tools, and finally interview level thinking. This roadmap is not just link, it is transforming you into someone who can actually design chips. Now let's place floor planning inside the full design flow. Imagine building a house. First you decide what kind of house you want, that's RTL design. Then you convert that idea into actual materials, that's synthesis. But before you start building walls, what do? You decide the layout. Where is the bedroom? Where is the kitchen? Where is the entrance? That is floor planning. In VLSI, synthesis gives you a net list, but that net list has no physical meaning yet. Floor planning is where you give it shape. Inputs come from everywhere. Net list, technology rules, timing constraints, power domains, package limits. And what do you produce? You produce a def file, macro placement, power grid, routing feasibility. Basically, you define the entire physical skeleton of your chip. Now here's the part most people ignore. The cost of a bad floor plan. Routing becomes impossible. IR drop exceeds safe limits. Clock becomes unbalanced. Wire length explodes. And worst case, you throw away the chip and start again. That's millions of dollars gone. So when you do floor planning, you are not just designing. You are making decisions that no one later can fix easily. Now let's zoom in and understand something fundamental. Before you place anything, you need to know your space. In VLSI, that space is divided into 3 key regions, the die, the core and the I/O. Think of it like this. The die is your entire property, everything exists inside it. Inside that, you have the core. This is where your actual logic lives. All your standard cells, your computation, your functionality, everything happens here. And around the core, you have the I/O ring. This is like the boundary wall of your house. It connects your internal world to the outside world. Now here's where things get interesting. You don't get infinite space. You have to calculate how much area you actually need. And that's where utilization comes in. Utilization is simply how much of your core area is actually used by logic. If you push utilization to 100%, what happens? You filled every inch with furniture. There's no space to walk, no routing, no flexibility. So in reality, engineers keep utilization around 60-70%. Why? Because wires need space, buffers need space, fixes need space. At advanced nodes like 2 amp, utilization drops even more. Because design rules are stricter, routing is harder and margins become critical. So remember this, empty space is not wasted space. It is what allows your chip to actually work. Now let's talk about shape, not size shape. This is where aspect ratio comes in. Aspect ratio is simply height divided by width of your core. Sounds simple, right? But the impact is massive. Imagine a very tall and narrow room. Walking horizontally is easy, but vertically, you're walking long distances. Now imagine a very wide room. Vertical movement is easy, horizontal becomes painful. That's exactly what happens with routing in chips. If your design is too tall, horizontal wires become long. If it's too wide, vertical wires become long. And long wires mean what? More delay, more power, more problems. That's why most designs try to stay close to a square shape. Now here's where engineers become precise. They don't guess dimensions, they calculate. Given total cell area and utilization, they compute required core area. Then using aspect ratio, they derive width and height. This is mathematical design, not trial and error, because once you lock this, everything downstream depends on it. Now we enter one of the most strategic parts of floor planning, macro placement. And this is where beginners usually make their biggest mistakes. Think of macros like big furniture, SRAM blocks, IP blocks, analog components. These are not small, they dominate space. Now imagine placing a huge cupboard right in the center of your room. What happens? You block everything. Movement becomes difficult. Space becomes inefficient. That's exactly why the first golden rule is this. Push macros to the edges. Keep the center open. Why? Because routing needs free space. Now comes the second rule, channels. Between macros, you must leave enough space for wires to pass. If you pack macros tightly, routing tools will struggle later. Third rule, alignment. If two macros communicate heavily, place them close and align their pins. Otherwise, wires zigzag across the chip, increasing delay. Analog isolation. Analog blocks hate noise. So you isolate them. Physically separate them from digital switching regions. Power domains. Each power domain must be continuous. You can't randomly mix them. So macro placement is not just placement. It's strategy, physics, timing, power and routing all combined. Now let's talk about something invisible but extremely powerful. Keep out zones, hollows, blockages. This is where you control what not to place, and honestly, this is what separates good floor plans from great ones. Imagine you have a heavy machine in a factory. Do you place workers right next to it? No, you create a safety boundary. That's exactly what a halo is. A halo is empty space around a macro. This space is reserved for routing, buffers and stability. Now blockages. There are different types. Hard placement blockage means absolutely nothing can be placed there. Soft blockage means avoid placing, but tools can override if needed. Partial blockage limits how dense placement can be. Routing blockage prevents wires from passing through certain areas. Now why is this important? Because without these constraints, tools will aggressively pack cells everywhere. And later, you'll face congestion, noise and routing failure. So remember this clearly. In floor planning, controlling empty space is just as important as placing components. Because what you leave empty defines how well your chip breathes. Now let's talk about how your chip actually talks to the outside world. Because until now, everything we discussed was inside the chip. But a chip that cannot communicate is useless. That's where I/O placement comes in. Think of I/O pins like doors and windows in a house. If doors are placed randomly, movement becomes chaotic. Same way, if I/O pins are poorly placed, routing becomes a nightmare. Now here's the first key idea. Pins must be grouped logically. If you have a bus, say 32-bit data, those pins must be placed together. Why? Because if they are scattered, routing those signals becomes long and messy. Next, power and ground pins. These are not optional, these are lifelines. They must be distributed evenly around the chip. And most importantly, they must be close to each other. Because large current loops create noise and instability. Then comes high-speed signals. Clock signals, sensitive data lines, these must be isolated. You don't want noisy signals interfering with them. Now there's also spacing between I/O ring and core. This is not empty by accident. This region is used for ESD protection and routing transitions. So I/O placement is not just connecting wires, it is designing how your chip interacts with the real world. Now we enter something that decides whether your chip even powers on correctly. Power planning. Think of your chip like a city. You need highways, distribution lines and local connections. In VLSI, power is delivered through a grid. Top metal layers carry large current across long distances. Lower layers distribute power locally to standard cells. Now here's the challenge. You must ensure stable voltage everywhere, not just near the power pads, but across the entire chip. Now how do engineers decide how strong the power grid should be? They calculate power consumption. Power is roughly P switching activity times capacitance times voltage acquired times frequency. From this, they derive current. And based on current, they design power stripes. Width, spacing, number of stripes, everything is calculated. If wires are too thin, they heat up. If too thick, they waste routing space. So it's always a balance. A weak power grid causes voltage drop. A strong grid consumes resources. So power planning is optimization. And without it, your chip is dead before it even runs. Now let's talk about something that silently breaks designs. IR drop. Imagine charging your phone with a long, thin cable. What happens? Charging slows down because voltage drops across the wire. Same thing happens inside a chip. When current flows through resistance, voltage drops. That's IR drop. Now there are two types. Static IR drop. This happens due to average current flow. Dynamic IR drop. This happens during sudden switching, like when thousands of gates switch at once. This is more dangerous because it creates sudden voltage dips. Now what happens if voltage drops too much? Transistors slow down, timing fails, logic behaves unpredictably. Worst case, the chip crashes. So how do we fix this? Stronger power grid, more vias, better distribution. And something very important, decoupling capacitors. These act like local batteries. They supply instant current when demand spikes. So remember this, you don't fix IR drop at the end, you prevent it during floor planning. Now let's talk about something even more dangerous, electromigration. And this is not immediate failure. This is slow death. Imagine water flowing through a pipe. If the flow is gentle, pipe lasts long. But if high pressure water keeps flowing continuously, over time the pipe weakens and eventually breaks. That's exactly what happens in metal wires. Electrons flow through interconnects. At high current density, they start pushing metal atoms. Over time, atoms move, voids form, hillocks form, and eventually the wire breaks or shorts. Now here's the scary part. Your chip works perfectly at first, passes all tests. Then after months, it fails. That's why electromigration is a reliability issue. Now how do engineers prevent it? By limiting current density, making wires wider, distributing current across multiple paths, and controlling temperature, because higher temperature accelerates damage. So electromigration is not just design, it is physics. And if ignored, your chip has a hidden expiry date. Now let's move into something that modern chips absolutely depend on, power domains. Imagine your house. Do you keep all rooms powered at full brightness all the time? No, your bedroom, kitchen, hallway, each has different power needs. Sometimes you even switch off entire rooms to save energy. That's exactly what happens inside a chip. Different blocks operate at different voltages and power states. These are called power domains. Now here's where things get tricky. When a signal travels from one domain to another, it cannot just directly connect. Why? Because voltage levels are different. That's where level shifters come in. They act like translators. They safely convert signals from one voltage level to another. Then we have isolation cells. Imagine turning off power to one room. You don't want random floating signals coming out of that room and disturbing others. Isolation cells block those signals. And then retention flops. These are like backup memory. Even when a domain is powered off, they remember critical data. Now here's the floor planning challenge. All these components must be placed at domain boundaries. You cannot scatter them randomly, and each power domain must be physically continuous. If you break that, power routing becomes a nightmare. So power domains are not just about saving power. They are about controlled, safe, intelligent operation. Now let's talk about something that saves your chip during sudden stress. Decoupling capacitors or decaps. Imagine this. You are using water from a pipeline. Suddenly multiple taps open at the same time. What happens? Pressure drops instantly because supply cannot react fast enough. Now imagine placing small water tanks near each tap. When demand spikes, these tanks supply water immediately. That's exactly what decaps do. Inside a chip, when thousands of gates switch at once, they demand a sudden burst of current. The power grid cannot instantly respond. This causes voltage drop. Decaps store charge locally and release it instantly. Now here's the key. Placement matters. If decaps are far away, they are useless. They must be placed near high switching regions. Engineers calculate required capacitance based on peak current, switching time, and allowed voltage drop. Without decaps, voltage fluctuates. Timing breaks. Chip becomes unstable. With decaps, your chip survives sudden load changes smoothly. Now let's talk about one of the most painful issues in physical design, congestion. Imagine a city during rush hour. Roads exist everywhere. But too many vehicles try to use the same roads. Result? Traffic jam. Same thing in chips. Wires are vehicles. Routing tracks are roads. Congestion happens when demand exceeds capacity. Now here's the important insight. Congestion is not created during routing. It is created during floor planning, poor macro placement, high utilization, bad aspect ratio. All these create hotspots. Now how do engineers fix it? They create routing channels between macros, reduce density in crowded areas, use higher metal layers for routing over macros, sometimes even shift macros slightly. Think of it like redesigning traffic flow. Add flyovers, widen roads, distribute traffic. Because if congestion is not solved early, routing will fail completely. Now we come to something that defines performance. Timing. Imagine catching a train. If you arrive late, you miss it. That's setup violation. If you arrive too early and the system is not ready, that's hold violation. In chips, signals must arrive within a precise window, not too late, not too early. Now here's the modern challenge. Wire delay is often larger than logic delay. That means distance matters more than ever. If two blocks communicate frequently but are placed far apart, delay increases. Timing fails. So, during floor planning, engineers identify critical paths and place those blocks close together. Now comes clock skew. Clock doesn't arrive everywhere at the same time. That difference is skew. And part of timing budget is reserved for it. If you ignore this, even perfect logic fails. So timing driven floor planning means you don't just place blocks, you place them based on timing criticality because performance is not fixed later. It is decided here. Now let's talk about the heartbeat of your entire chip, the clock. Everything we've discussed so far, logic, power, placement, all of it depends on one thing working perfectly, the clock signal. Imagine a school. There's a bell that tells every classroom when to start. If one class hears it late and another hears it early, total chaos. That's exactly what happens in a chip if clock is not properly planned. Now here's the key. During floor planning, you are not building the clock tree yet, but you are deciding whether it is even possible to build a good one later. First decision, where do you place the clock source? Usually a PLL, ideally near the center. Why? Because distance to all regions becomes balanced. That reduces skew. Now clock wires are special. They are wider, they are spaced more, sometimes even shielded with ground lines. Why? Because clock is sensitive to noise. Then clock gating cells. These reduce power by turning off clock to unused regions, but they must be placed near the logic they control, not near the source. So here's the insight. Clock planning starts in floor planning, not later. If you ignore it here, timing closure becomes painful. Now let's talk about something that doesn't affect normal operation directly, but is critical for testing. Scan chains. Imagine a factory. You don't randomly inspect products. You create inspection lines. Products move through checkpoints. That's exactly what scan chains do. They allow engineers to test internal flip-flops by shifting data through them. Now here's the problem. If you create one long scan chain across the entire chip, routing becomes huge. Delay increases, congestion increases. So what do engineers do? They break the chip into regions. Each region gets its own scan chain, shorter chains, less routing, better performance. Now scan input and output pins must be near edges, so testing hardware can access them easily. And scan chains must be balanced, same number of flip-flops, otherwise test time increases. So even test starts with good floor planning. Now before moving forward, your floor plan must pass something critical. Physical verification. Think of it like building inspection. Even if everything looks good, you must check rules. First, geometry. No overlaps. Proper spacing, everything aligned. Then connectivity. Power and ground must be continuous. No break. But here's the twist. Just being connected is not enough. It must also be strong enough. Then density. Metal must be evenly distributed, otherwise manufacturing fails. Then antenna checks. During fabrication, long wires can accumulate charge and damage gates. Then pin accessibility. Can routing tools even reach all pins? If any of these fail, you go back and fix, because fixing later is much harder. Now let's move into advanced nodes. This is where things get extremely difficult. Imagine building in a crowded city. Space is limited, rules are strict, precision is everything. That's what happens at 7 nm, 5 nm, 3 nm, even 2 nm. Routing tracks become smaller, spacing rules become tighter, variability increases. Now here's something new. Backside power delivery. Instead of routing power on top layers, power comes from the backside side of the chip. This frees routing space, but adds new constraints. Now you must reserve regions for vertical connections and manage new design rules. Also, EUV lithography introduces variability, so density must be controlled very carefully. That's why utilization is reduced at advanced nodes. So floor planning here is not just design, it is constraint management at extreme limits. Finally, let's talk about hierarchical floor planning. Because modern chips are too large to handle as one block, imagine designing an entire city. You don't design everything at once. You divide it into zones: residential, commercial, industrial. Same thing here. A chip is divided into blocks: CPU, GPU, memory, IO, etc. Each block is floor planned separately. Each gets its own area, constraints, and timing budget. Then all blocks are integrated. Now here's the challenge. Coordination. If one block grows in size, everything shifts. If one block misses timing, entire chip fails. So interface pins must align. Timing budgets must be distributed properly. Hierarchical floor planning allows scalability, but requires careful planning because everything must fit together perfectly. Now let's talk about something invisible but extremely dangerous. Signal integrity. Imagine two people talking in two adjacent rooms. One person is shouting loudly, the other is trying to speak softly. What happens? Noise leaks. Communication gets disturbed. That's exactly what happens inside a chip. Wires are placed very close. When one wire switches fast, it creates electric fields. Those fields interfere with nearby wires. This is called crosstalk. The noisy signal is called aggressor. The affected signal is called victim. Now what happens if noise is too high? Wrong logic value. Timing failure. Unpredictable behavior. Now how do we fix it? Spacing between wires. Shielding using ground wires. Separating sensitive signals like clocks and isolating analog blocks. So signal integrity is not just routing, it is controlling noise at the physical level. Now we move into sign off. This is the final checkpoint before your chip is declared ready. Think of it like final inspection before opening a building. Everything must be perfect. First, geometry. No overlaps. Correct alignment. Correct die size. Then power integrity. Power grid must be continuous. IR drop must be within limits, typically within a few percent. Electromigration must be safe. Then timing feasibility. Critical paths must be achievable. Then congestion. No region should be overloaded. Then multi-voltage checks. Power domains must be correct. If anything fails, you go back. Because after this, fixing becomes extremely expensive. So sign off is not just checking. It is validating that your chip will survive real world conditions. Now let's talk about something very important. Reality check. Your floor plan might look perfect on paper, but can it actually be implemented? That's what early analysis answers. Engineers run congestion estimation, divide chip into grids, check demand versus capacity. If overflow appears, routing will fail. Then timing estimation. If delays are already high, placement cannot fix it. Then clock feasibility. Is there space for buffers? Is a skew manageable? Then scan feasibility. Are test structures realistic? So this stage answers one question. Is your design practical or just theoretical? Now let's connect everything to real-world design thinking. Imagine designing a smartphone chip. CPU needs high performance, so it must be placed close to cache. GPU consumes high power, so it is placed where power delivery is strong. Memory interfaces must be near edges. Because they connect outside, AI accelerators must be close to data sources. Every placement decision is based on performance, power, and connectivity, not random. One wrong placement can increase delay, power, and temperature. So real flow planning is like solving a multi-dimensional puzzle. Now let's talk about tools. Tools like Innovus ICC tools, they are extremely powerful. But here's the truth, they don't design for you, they execute your decisions. You define core size, utilization, macro placement, power grid, constraints. Tools follow. If your plan is wrong, tools will create a wrong design faster. So tools are assistants, not decision makers. Understanding is what matters. Now let's think like an interviewer. They won't ask definitions, they'll ask scenarios. Like, how do you place multiple SRAM macros? You start with fixed blocks. Place largest macros first. Group related ones, align pins, leave routing channels. Or they ask, routing fails due to congestion. What do you do? Reduce utilization, add blockages, move macros, create channels. So interviews test thinking, not memorization. 7 now comes the most important concept in engineering, trade-offs. You cannot optimize everything. Increase utilization, area reduces, but congestion increases. Wider power stripes, better reliability, but less routing space. Close placement, less delay, but more congestion. Spread placement, less congestion, but more delay. Every decision affects something else. So engineering is not about perfection, it is about balance. Now we move to system level thinking. This is where you think beyond just design. Think long term. Temperature increases resistance, leakage increases, electromigration worsens, hotspots appear, so you distribute power blocks. Avoid clustering. Consider worst case scenarios, not just typical cases. Also consider latch up, unwanted current paths, prevented by spacing and guard structures. So this is designing for reality, not ideal conditions. Now let's talk about formulas and intuition. Formulas guide you: utilization, cell area, core area. Power equations define current. IR drop I times R. Electromigration depends on current density. Timing depends on delay RC. Congestion depends on demand versus capacity. But here's the key: you don't just use formulas, you combine them. You predict behavior before running tools. That's when you become an engineer. Now the final truth. A great floor plan is invisible. No major issues, no chaos. Everything flows smoothly. Routing completes, timing closes, power is stable. A bad floor plan, endless problems, debugging never ends. So floor planning is not just a step, it is the stage where you decide success or failure. If you master this, you don't just place blocks, you design chips with intent. And that is what makes a true physical design engineer.